Let's talk about the Tesseram parameter, which is an approximation for the Jacobi constant in terms of the orbital elements. As important as the Jacobi constant is, being the only conserved quantity of the three-body problem, it's written in terms of the positions and the velocities. So an expression, even approximate, in terms of the orbital elements is usually very useful to estimate the change in the orbital elements after a passage, say, by a planet. So this shows here the orbit of a comet after a close encounter with Jupiter. The comet was in its orbit here, and then it had a chance encounter with Jupiter that changed its orbital elements. During this encounter, the Jacobi constant is conserved, and the Tisserand parameter is a good approximation for the Jacobi constant. It relates the semi-major axis, the eccentricity, and the inclination. The conservation is not perfect. Here you see for eccentricity of Jupiter equals 0, the Tesseram parameter before the encounter and after the encounter. So it varied, but it's slightly around the same number, variation of percent. Same thing here for a higher eccentricity of Jupiter, 0.048. Pass from this level to this level. Again, this oscillation here is the orbital period of Jupiter. So let's see how we get to the Tesseram parameter from the Jacobi constant. All right, so let's write the Tisserand parameter in the co-rotational frame. And let's consider then that we can transform these velocities from the co-rotational frame to the inertial frame. In the inertial frame, we reinstate the velocity of the planet, and then the Jacobi constant becomes, you can write the equation for the energy and solve this for the velocity. This equation assumes the mu is equal to 1. Now consider the angular momentum, which is r cross r dot. So the z component of the angular momentum is equal to x y dot minus y x dot. And the z component of the angular momentum is the vector angular momentum dotted with z hat, which is L cosine I, where I is the inclination. The magnitude of the angular momentum is given by the semi-major axis and the eccentricity. So we can substitute this Lz into the Jacobi constant and write it in terms of the angular momentum, where we substituted also the equation for v squared. Now we make a series of approximations. First, we assume again that mu1 is equal to 1. And the mu2 is much, much less than m1, and we can assume this will be 0. So we can get rid of this second term here on the potential. And because mu1 is equal to 1, so is the Keplerian frequency. So this is equal to 1, and this is equal to 1. So the 2 over r and the 2 over r here are going to cancel. We can therefore write an approximation for the Jacobi constant as equal to twice the cosine of the inclination times the square root of the semi-major axis times 1 minus the square of the eccentricity plus 1 over 8. And this is the Tisserand parameter. It's half of this approximation of the Jacobi constant. So this is an approximation. It has its uses, but have to keep in mind the differences between this and the Jacobi constant. First, the Jacobi constant is in the co-rotational frame, and this is in the inertial frame. I mean, you can also define the Jacobi constant in the inertial frame, but the Tisserand relation is only defined in the inertial frame. And the approximations that were done here, you assumed that mu2, so the mass of the planet, is much, much less than the mass of the star. And you're using units such that the mass of the star and the Keplerian frequency of the planet are equal to 1. You essentially set mu2 equal to 0, which is where most of the error in this approximation is coming from. But again, this is a very useful estimate, even though it's a little bit crude. It can be used to determine whether or not, say, a newly discovered comet is a previously known object that has had its orbital elements changed by a close approach to a planet.